But CAP theorem has a problem which is very straightforward because CAP only talks about what happens during a partition, right? Don't know what to choose when there is no partition, and partition happens rarely. Like, I know partitions are inevitable, unavoidable, but we don't see partitioning happening 99% of the time. So, is the problem remain same that when there's no partition, should we still choose C or A, like consistency or availability? No, but partitions are rare. We just learned, right? Most of the time it works. So, what trade off exists when everything is healthy? I mean, there's no partition. What should we do then? This question led to PACELC theorem, which is like advanced version of CAP theorem. Now, Stitch is saying, what the heck is this PACELC now? We'll learn this. So, PACELC theorem is very simple. PACELC theorem was coined by this guy called Daniel J. Abadi. He he's the guy behind VoltDB. He's a Yale professor, and he said that CAP theorem is incomplete. CAP theorem talks about what happens during partition, but in reality, partitions are rare. While trade-off happens, most of the time we don't talk about it, right? So Packel says, if partition, choose availability or consistency, which is the first three letters, PAC, partition, choose availability or consistency. Else, choose latency or consistency. Now that's a drop. I mean, there's the change that Daniel said that during partition, go with cap. When there's no partition, go with Packel. So let's see some example. Let's say Dynamo or Cassandra. These two DBs are very popular. They chooses PA and EL, which is during partition they go with availability, and during no partition they choose latency, which is like low latency. The system picks availability plus latency or strong consistency. That's why they offer eventual consistency by default. That doesn't mean that they don't offer consistency when there's no partition. You can always tune it. You can always change the configuration so that your DynamoDB or Cassandra DB is still choosing consistency when there's no partition. But that's a different discussion altogether. Now, the Spanner database of Google, Spanner is like the primary database that Google uses. It uses consistency in both situations. If there's a partition or there's no partition, and it prioritizes consistency all the time, thanks to two time clock. You can always read about it. What is two-time clock? It's a very interesting concept. And then MongoDB. MongoDB, I personally worked a lot with MongoDB when I was building this startup, and it's configurable. It's very nice. You can tune the read-write consents, which can lead to PA, EL, or PCEC. I mean, either choose consistency all the time or choose availability during partition and latency otherwise. So when we say low latency, I mean, there's the trade-off between latency and consistency should be clear. Why there's a trade-off? Because when we want to bring all the system in a consistent state, that means we want all the replicas of our primary database or primary server should be replicated. I mean, all nodes have same data. That takes good amount of time. When you want all the system to be consistent in a single transaction, in a single request, you can't guarantee low latency. When we say low latency, we means sub-millisecond latency, which is like real-time latency, which is less than 200 millisecond or less than even 100 second. Which, I mean, this kind of latency we consider it real time because we can't measure the difference between a sub-millisecond latency, right? We feel like, let's say it's a real time change happening, but the latency is like 100 millisecond or 200 millisecond. Why it matters in system design interval? That's very important to know. Let's say if you're asked what happens when the network partition, what happens when the network partition happens? That's CAP theorem, right? Another question could be, what trade-off exists when the system is healthy? That's PACELC theorem, right? Which is like latency versus consistency. For example, in social media, feed might choose low latency because showing stale feed is completely fine, right? Nothing to lose. But a payment system at the same time will choose consistency. We learned about this ATM and the bank example, right? Where showing correct balance is way more important than guaranteeing low latency. So now you know why CAP and PACELC theorem lays the foundation of system design interviews. Because whenever you're asked to design subsystem, let's say design WhatsApp, Uber, Amazon, Google Doc, these kind of questions can be asked and should be asked to your interviewer, like when the network fails, what should our system do? Should we prioritize consistency or availability, right? These kind of choices one should make. So in short, CAP is the trade-off during failure, which is like partition, network failure, and PACELC is the trade-off is always, I mean, PACELC has CAP theorem in it, Like it's an advanced version, or it's a, let's say CAP is a subset of it, right? So it considers both network partitions and the normal case when there's no partition. So now these are the very important things that one should remember. Let's see some simple analogy to remember CAP and PACELC theorem. Imagine you have two gossip groups, one in hostel A and one in hostel B. Set of college friends in group A and group B, both in different hostels. So let's say partition occurred. The partition here could be summer break, semester break. I mean, these two friends group are separated. Now they are at their home location. I mean, they are at home. So they have two options. Now these two groups were used to gossip in the college whenever they used to meet. Now the option is they can stop gossiping until the reunion. Reunion as in when they come back to the college, which is like maintaining high consistency. Everyone has the same information before and after the partition. Or keep gossiping locally, like within the group, and then deal with the confusion later, which is like high availability. I mean, the group within it is still discussing, like both the groups within themselves they're discussing, but they're not discussing with each other, the two group. So intercommunication is there, but no direct communication. That's CAP theorem. And when even there's no partition, and then they are in college, they are meeting it regularly, daily, they still have a fair choice. One is talk fast, but risk the misheard details. Now each friend can be considered as a node, right? They're talking so fast, so but at the same time, the problem is a lot of nodes could, I mean, a lot of friends could, I mean, a lot of information might go misheard. They're prioritizing latency first. They're talking so fast. At the same time, the other option is talk slow, talk carefully, so that everyone agrees on the fact, everyone knows what we are talking, which is like maintaining the consistency first. So now we have a clear idea of what needs to be discussed during an interview. Whenever you are given to solve or design a problem, let's say design WhatsApp, you can ask when there's a partition, should the system prioritize high availability or consistency? And when there's no partition, should we prioritize still on consistency or low latency? Before ending, I want to fret again on the PACELC theorem, because I still feel there could be some confusion between the L and the C, which is the latency, low latency versus the consistency. And this is one of the most important lesson in distributed system, right? I believe it is most important, because strong consistency means communication, and each node are communicating with each other. Communication means they are waiting for the other to reply. Waiting means latency, right? Let's say there are three nodes, one in North America, one in India, one could be in Dubai. All the three nodes, to stay consistent, when I say consistent, I mean all the data that they are storing are same. I mean, they don't have any disagreement. They all have the same data at any point of time, which is whenever there's an update in, let's say, Dubai server, it has to be replicated to what? North America and the India database, which means one has to wait till all the data are in sync, which is latency. And that's why, I mean, all the network round trip to make every node in a consistent state will take some time, right? So your latency increases. Your latency just increased because of this, like maintaining the consistency within these nodes. So that's why strong consistency isn't free. It comes with high latency. So you pay with the speed, the latency. At the same time, when you don't guarantee strong consistency, you can asynchronously sync your replicas or the other servers, right? But at the same time, you can serve quickly. I mean, low latency, you can serve the stale data. It's fine. You have to make this trade-off that I am serving stale data, maybe, and I mean, I'm giving a best effort response. And after some time, we might give you the correct one, because the data is still getting synced with the other servers. And I hope this is clear now. And thank you so much. Thank you so much for watching this video. Stay tuned. We'll be coming up with more time deeps in system design. I'll be also taking up some system design interview problems. And the next one I'm planning is to design distributed rate limiter. See you. Bye bye. Take care.